This webinar, which is about why 0.1 second matters in IoT. And you can say matters in IoT. Well, it doesn't matter only in IoT. It actually matters in all kind of respects, and I'll get more into that. So this is not only IoT, and it's not even only IT application that it matters for. This will be the agenda, two short parts. So one part is about the speed. I mean, why latency? Why does that matter? And it will mostly be about human psychology and human nature. Some rules that somebody called NN Research has found out, and some examples of real world examples where I can show that this is actually something people they will write about. So reviews of apps showcasing that this is not something just from research or something I'm saying. It's actually something that is you can go out and you can find real life examples that support this. The next part is trying to look at two types of IoT. The cloud IoT type, which is pretty well known, since that's what all the big companies, Microsoft, Amazon, Google, they push this type of IoT because they want to sell the cloud. Some thoughts on ping times and real world ping times, where we can show what is the kind of network latency that we see on a normal network in today. It's data that is pulled from this month. And then something on IoT device limitations, and last, we'll explore this peer-to-peer IoT, which is another way to do IoT, and how that can actually solve some of these limitations, and then a short Q&A session. So again, responsiveness matters. This is not something we have researched. This is something actually now this says 1997, which is already more than 20 years ago. Jacob Nielsen is from something called NN Group, which is a research team doing user experience research. And some of this is actually from some results that is from the 1970s. But basically, responsiveness matters because of human limitation. It has nothing to do with computers. It's just our brain is, 300,000 years old, and has been developed for something else than sitting in front of a computer. And we, as humans, we have limited memory and attention spans. If you have kids, you will know all about that. The issue is, if you do a request, you have to wait until you get the response to actually delete that request from your memory. And since humans have a fairly short memory and attention span, it matters that the request and the request and the response actually are very close in time. So you can say that's one of the issues. And the next is what he calls human aspiration. Humans just like to feel in control. So even though it is a computer, people know it is a computer, they're responding from or asking for something, they will quickly feel like the computer is arrogant or incompetent if the computer doesn't show a response fairly quickly. The people have built this times 10 time rule. Again, this is not something we are saying. It's something you can find in research, fairly old research. And I actually think that this has just, you can say, gotten worse. People today surfing the web might not even think that 1 second is okay. But basically, what it states is that if you're in the 0.1 second range, people feel like they're interacting in real time with the device. And you also know that from movies. I think a movie showcases 24 pictures a second, and we are kind of in that range with 0.1 second, that people feel that this is in real time. So if you're under 100 milliseconds, the user feels like, I mean, this is in a real time flow with the system. But already when you get up to 1 second, people begin to feel that I now push a button and I have to wait, and then something returns to me. And as I say, I actually think this today is probably even worse than 1.1 seconds, and that's because I sometimes I look behind. I stand behind a junior developer, and I see how they surf the internet, and they can sometimes they'll just open 10 tabs. And the fastest tab that gives them a response, they go look at that response, and all the other tabs will just close. So actually today I'm not even sure that 1 second is enough. I mean, if that's enough of a limit, and then of course we have something like 10 seconds, and today that's even though 10 seconds doesn't sound that much, if you're waiting on a web page for 10 seconds, you will get pretty annoyed. And especially as I return to this, if you're standing out in the rain and you try to open the smart lock on your door, or you try to disable your alarm system, 10 seconds is way too much. Even 1 second is too much, but that's another thing. So again, I mean, this is something, and it is research driven. These user interfaces, responsiveness in user interfaces and in interaction with a device matters, and I think that we have just been okay with that in the start of the IoT period, because we went from no communication to some communication. But I think in the next years we'll see that people are starting to require much better user interfaces, and this is a good example on this. This is I don't want to to tell who it is, but it's a smart lock, a very well-known big company that has made a smart lock, and some of the reviews are just saying, well, this is too slow. I try to connect to the smart lock, and when I try to open the door, I have to wait for too long. And again, this just gives you 1 and 2 stars on App Store. So this is not just something just I'm saying, or just the research is saying. This is something you can go out and you can review on some of these app store reviews of slow apps. People today are demanding that you have the same kind of user interface that you see on other apps on your phone or other apps on your PC. And it's not just good enough that you can actually access and remote access it. It has to be just as fast as all the other apps you have on your phone. So you can say the conclusion, and this is actually again not even me or us saying this. This is again from this NN Group research. When you do a UX design, speed must be the overriding design criterion. You have to first make the user interface very snappy and low latency. Then you can go with all the other bells and whistles and look at the color and how it's designed and so on and so forth. Speed is the overriding design criterion. And again, this is not something I say. This is actually very, very high-end research people. Let's look at some of the IoT systems out there, and one of the type of IoT that we see again and again and again being pushed to us is this type of called cloud IoT, which basically consists of an IoT device a cloud application, and of course the IoT client being the smartphone or your PC or your tablet that you control and you want to remote access your IoT device with. So once you send a command to a device in a system like this from the phone, it will first go from the client to the cloud application. And this already introduces some latency. You have to encrypt the data, you have to decrypt it on the cloud, you have to process it on the cloud, find the right connection on the other side, and store and forward it to the IoT device. And then, of course, all this goes the other way when returning to the client. And sometimes it actually also have to be stored in a database. And this, of course, only makes it even worse. But sometimes it's also just store and forward. And if we look at some ping times today, this is something that you can go out, you can use this site called Wonder Network. You can go and you can try to make a table of what is the ping times between different locations on the internet. And this, and people sometimes say to me, yeah, but this will be better. I mean, it's getting better all the time. No, because we are approaching the speed of light. And even though the speed of light is very, very fast, you have to remember first of all, the speed of light, when people hear 300,000 kilometers a second, that's in vacuum. But we are not sending light in vacuum. We are sending it in fiber, what's it called, network fibers. And that already, which is glass, and that's another medium than what's it called, vacuum, and that already slows down the speed of light. So we are approaching. I mean, this can get a little better, but again, there's a limitation on how fast we can, how much better it can be. So already now you can say you'll if this 0.1 second is important, you cannot place the cloud in a different on a different continent. So today you can go to Amazon and you can boot up a server, but if your customers is in Frankfurt, they need to be located on a server system that is close to Frankfurt, because if it's in Los Angeles, it's already more than 0.1 seconds away, and it just gets worse if we go to Asia, and for that matter also if we let's see. Just the New York to Washington. Okay, that's fairly quick. But Los Angeles to New York, we already on a 0.08 second. And again, this is, I mean, raw network traffic, no encryption, direct, and on very, very fast servers. So this is very fast computer to a very fast computer going back and forth. Again, if we look at the IoT side of this, or the IoT device side of this, we have to remember these are not very fast computers. You have to, just like in all other computers, you will have a network interface. You have to encrypt and decrypt. You have some logic that has to compute something, and then you might even have to send out a command to a sensor or actuator, sometimes via Zigbee or something else that also introduces latency. And if we look at the parts here on one of these small computers, compared to, for example, a PC or smartphone, a lot of times the network layer is on a module of some kind, and then you have to transfer that. So the data gets into the network. Let's say it's a Wi-Fi or it's an Ethernet module, and then you have to transfer it to you can say the operating memory. And a lot of times this has to be done via serial or similar. And it's not. Sometimes it is a direct memory access. So you have hardware that will move the memory, but a lot of times what we see on especially the small IoT devices, this all has to be done with the fairly slow CPU or microcontroller on the system. It has to be decrypted, and again, it's on these small microcontrollers, and normally it's not hardware assisted. If you look at PCs and also smartphones, they have hardware to actually help you with the encryption and decryption. Actually, in the x86 command, there's actually opcodes where you actually have hardware assisted AES encryption and decryption, but not on these small microcontroller. It has to be manual handled. It has to do the task, to create the result, encryption, network I/O, and again, all this introduces a lot of latency into the final application, and this is even without looking at what kind of latency will the cloud introduce. So another way to do this IoT is what we call peer-to-peer IoT, or real-time IoT, and you use the same technology as Skype or Teams and Zoom, what we're sitting on here right now, to create direct connections between the two entities. So instead of having the cloud to be a store and forward, you can actually create a direct connection between the IoT device and the IoT client, and they can send commands and requests directly to each other, even if they are on a local area network. And you can say, I mean, how hard can it be to actually create a connection from a client to a device? But that can be pretty hard today. When I started on the internet, I would say ages ago, if you had an IP address, you could connect to that IP address. That's not how it is anymore. You have firewalls. You have dynamic IP addresses so devices, even though they are stationary, they move around on the internet, getting a new IP address all the time. Then you have the issue of managing IPv4 versus IPv6 addresses and connecting between them, and also, of course, the basic issue of security. Even though if you get a connection, you also have to think about who is on the one side, who is on the other side. And all this has to be handled by these two. Again, this direct connection, of course, removes a lot of the issues, but of course not all of them. The IoT device, is still a slow IoT device, but using peer-to-peer IoT, at least in our platform, we use something called DTLS, which is a very simplified network protocol. And if you look at it, what's it called? The certification of the Internet standard says that DTLS is what you should use for IoT encryption, and that's because it's packet oriented instead of having TCP on top of the network layer. You of course get the fastest network path. You go directly from A to C instead of going up in the cloud to B and back to C. And then of course you skip the latency of the cloud servers. And I hear a lot of times people say, yeah, but we have measured how fast cloud servers are, and we can see that, okay, the latency of cloud servers is not that much. And that's correct if you only have one device connected. But if you have, like, let's say 100,000 devices connected, maybe even millions of devices connected, then suddenly you will introduce and you will see latency in the cloud servers. And especially if you also have to do database access when you are doing all these commands, then the latency will go higher very, very fast. Low latency and responsiveness is actually not the only good thing about IoT, but I'm only going to cover this here. But I'll just briefly touch on some of the other reasons why people should look at peer-to-peer IoT. And one of them is it's very simple to develop apps with it, because you only have it's just like a client server setup. You don't have the cloud where you also have to manage both the cloud and the IoT device, and of course the client. Here you create a connection, you send a command, it will very fast go back with a result. You don't have to make asynchronous user interfaces waiting on these results to come back. So it's very simple to make user interfaces with this. It offers very, very high privacy and security. Since nothing is stored in clear text on other than the IoT device and also on the IoT client, the end user is always in control of his data. It's very, very scalable and cost efficient. Again, because of course you use cloud servers to create these connections, but once you have created the connection, it's all being handled. All the computing and all the compute power is handled on the IoT device and on the IoT client. And then of course you also have the local network only support. So let's say you are shortly being disconnected from the internet. Your ISP connection breaks down for some reason, and you are actually in your own home, and you have a local area network that is connected, has connected both your IoT device but also your IoT client, being the smartphone. If you are using cloud IoT, you don't have access to the cloud, so you cannot store and forward data through the cloud anymore. So actually, you even though you're standing right beside your internet device with your smartphone, you cannot connect unless, of course, you do something else. Basically, having a system just like this. In this type of technology, it's fairly easy because I mean, you have the simplest network, and you can just create a connection directly by discovering it, by discovering the two parties over a broadcast on a local network. So this type of system will work if you are shortly disconnected from your ISP and you're sitting in your home and you want to control your lighting or your smart lock or whatever. Whereas if you use cloud IoT, this can be an issue. So again, a very short presentation on why latency matters in IoT. And if you have some questions, you are very, very welcome to send them. We'll try to answer.
Yeah, sure, Karsten. So actually, I have one question regarding that ping. So, for example, if I want to ping the Nabto cloud, right? So, is there, I mean, any way directly we can check the latency between the device and the Nabto cloud?
Yes, when you get a connection, you can actually ask the device layer, the software layer, what type of connection do we have? Because the platform will start measuring what is the connection speed between the two, which is normally used for. So if you stream data, you need to know what is the kind of latency because you have to calculate. Let's say if you have a buffer, streaming buffer, you have to calculate how fast can I send the packages. So actually, yes, the application layer on both the client side and the device side will know what kind of latency is on the both. It will know the latency of the connection, but it'll also know the speed of the connection. How much throughput can you actually get?
Oh, okay. So throughput we can measure via Wireshark, right? I mean, what is the request we are sending? That request and what is the response we are getting from the Nabto? By this we can measure the latency, right?
Yeah,
Using why
the
by
client and device
capturing
will
the
know that.
packets. Mhm.
The client and device will both know the latency of the connection, but also the throughput, because again, the throughput can vary a lot.
Yeah. Okay. It
It's
depends
not
on the
just your
network.
Wi-Fi
Yeah.
network that
Yeah.
sets a limit. It can be your router can have a small buffer, and all the you can say the transition points on the route from A to B have an issue. So it's actually very hard to find out what, and you can only find out the you can say the throughput of a channel by actually starting to send out packages, and then you'll, just like a PID controller, you'll find out, okay, this is the amount of throughput we can get on this.
Okay, yeah, thank you. And I have a couple of more questions. I think
Yes.
this is not regarding to whatever the slides you have explained, but it's more about the Nabto, the enterprise edition and the trial version.
Yeah.
Okay, so one first question is regarding the in trial version. What I'm trying is currently we are going to, I mean, use the Nabto with our 5G networks. Okay, so in our product, we are trying to integrate it with Nabto, and we want to see the RTSP streaming over the Nabto by creating this by using this Nabto. So what we are trying is currently we are testing it by using this trial version. So in trial version, we are adding this product ID and device ID into our device configuration file manually because we are using the trial version, right? So for this enterprise version, do we get? I mean, it will be product ID and device ID, and whatever the device we are going to use, there will be a lot of many devices in our
Yeah.
production. So it will be
I
done
think this we
automatically.
need to, yeah, we need to get the CTO Ulrich to answer this, because there's a lot of on the production version, there's a lot of you can download batches for as a file, and then you can flash in production, you can flash the IDs, the product IDs, and all this. But again, I'm not uh, I'm more high level on the technology here. We need to get Ulrich, our CTO, on this.
Okay, so I mean, at the time of manufacturing this unit, we can flash this product ID and device ID hard coded to the particular device,
Yeah,
right?
and also you can
Hmm.
download. There are tools so that you can create. You can say batch files where you have the product ID and also the keys and everything, so that
Okay,
your production system can take the next line, find the product ID, um, the keys, and yeah. And again, sorry, I'm but
uh,
yes, there are facilities there are facilities and tools where you can get these production batches that you can send directly to a production, and it can work through the files, and instead of communicating with the cloud.
okay, okay. Thank you very much for this information. Yeah,
Yep.
this is only from my side.
Yep.
Yeah.
Super.
Carson, we got some inquiries while you were doing the presentation from people that had signed up. They unfortunately couldn't make it, but luckily we are recording this, so I'll make sure to send this out to everybody.
Yep. Great.
So they have a copy so they can get this great information. I just quickly, I just wanted to ask, I mean, how long does it usually take for a company to secure and speed up a IoT transmission? Does it vary, or is there a good general answer for that usually?
It depends. Again, if it's a Linux system on the device side, we have demos where you can basically compile it yourself in, I don't know, a day, half a day, and you have a demo app up and running. Of course, just showcasing how it works, but you have to do all the other integration yourself. But you can have something up and running in half a day if it's I would say a Linux system, a Linux device. It's a little more complicated if it's a real embedded, as you call it, so a real-time operating system like FreeRTOS or FredX or similar. But that's general to the industry. It has nothing to do with our software. It's more real embedded systems are just much more harder to code and program. But also, of course, the price is smaller because it's the microcontroller is smaller, the memory is smaller, everything is smaller. So it's normally a trade-off on variable cost versus you can say development cost.
Okay, interesting. Well, that sounds great. Obviously, I know this technology optimizes the connection and saves significant money and time. So I know that a lot of people can benefit from this, a lot of companies.
Yeah.
Mayor, did you have any more questions for us?
No.
Okay. Well, I'll definitely, so thank you, Mayor. I'll definitely, Carson, thank you once again. I'll make sure we'll make sure to send the video recording to everybody, and they have our contact information if they have any questions after seeing the video as well. We can make sure to answer their questions. And then we'll just go from there.
Let's do that. Thank you very much.